Theorists claim the Big Bang was not the beginning. First hints are emerging of a universe that existed before our own, an alien world of chaos where time, space, and geometry were yet to form. We are told it was big, yet it was probably unimaginably small. We are told there was a bang, yet there was apparently no sound and no space for anything to explode into. Some think it might have happened multiple times, so even its definite article is not doubt. Definite article is in doubt. Now, although everyone has heard of the Big Bang, no one can say confidently what it was. After all, recounting the beginning of time is about finding not just the right words, but the right physics. And ever since the Big Bang entered the popular lexicon, that physics has been murky. Perhaps no longer, thanks to an unusual way of delving into our universe's backstory that has emerged over the past few years. In this view, the essence of space and time can exist beyond the confines of the cosmos, but in a state of roiling chaos we would not recognize. The Big Bang is not a hard and fast beginning, but a moment of profound transformation, one quite different from anything most of us could have imagined. Though often misattributed to the US astronomer Edwin Hubble, the basic idea of the Big Bang dates back to the Belgian priest and astronomer Georges Lemaitre, who observed in the late 1920s that the universe is expanding. Extrapolating backwards, Lemaitre imagined a primeval atom that ballooned into everything we see today. That was this primeval atom. What was it? Where did it come from? Such questions cannot be posed without some trepidation. Stephen Hawking famously argued that asking what came before the Big Bang is like asking what is north of the North Pole. Since time itself was created at that moment, he reckoned the question of a prior origin is meaningless. But that has not stopped physicists from trying to pick it apart. Lemaitre himself floated the possibility of a phoenix universe, whose expansion shows, reverses, and ultimately collapses into a new primeval atom before bursting outwards into life once again. A more elaborate version of this cyclical story was proposed at the turn of the century by Paul Steinhardt at Princeton University, Neil Turok, then at the University of Cambridge, and others, in their ecpyrotic hypothesis, the name derived from ancient Greek word for conflagration. An early speck of our universe drifted around in another dimension, eventually smashing into another universe, liberating untold energy and sparking explosive growth. Wild as that may sound, some proposals get wilder. Take inflation, a widely supported theory that supposedly explains how primeval atom blew up from something infinitesimal before expanding at the more leisurely pace we see today. This growth spurt was instigated by a random fluctuation in the quantum field, and something similar could happen at any time and any place. That not only means that other universes could be invisible, branching off from ours, but also suggests that our own universe could be one branch of an infinitely old multiverse. Yet whether we invoke ecpyrotic collisions or infinite inflation, attempting to demystify the Big Bang as a moment that recurs throughout eternity does not get us any closer to describing exactly what happens in that key moment. The Big Bang was born from our best theory of gravity, general relativity, of Einstein. Here, space and time are unified as space-time, the invisible canvas of reality. Stars and planets deform space-time, and this warping creates the pull of gravity. We know from astronomical observations that space-time is expanding, and so according to general relativity, it must once have been an infinitely tiny, infinitely dense point known as a singularity. That's nice and neat as far as it goes, but it stops short of describing all the stuff within space-time, stuff that is governed by quantum theory. This most successful theory deals with the small yet infinite particles and chunks of energy Finite is the operative word here. Rewind the quantum universe and you see galaxies collapse as stars unborn and atoms dissociate into their nuclei and attendant electrons. When space is very tight indeed, you see signs that all nature's forces, bar gravity, unify into just one. But that force still comes in chunks, and that is as far as quantum theory can take us. It can do incredibly small, but unlike space-time, it cannot diminish smoothly to zero. This conflict is what makes understanding the Big Bang so tricky. For the past few decades, the obvious way forward has been to develop a quantum theory of gravity. That entails unraveling the inherently continuous space-time canvas into discrete threads, atoms of space, as Bai Lok Hu, theorist at University of Maryland, calls them. In one popular theory, loop quantum gravity, these atoms of space are loops of nothingness defined by mathematics. There are other options too, but most focus on describing the atoms of space accurately in the assumption that a coherent quantum description of space-time, including the Big Bang, will then fall into place. Who believes that's optimistic? That last step is made out of the straightforward, he says, it isn't. Nebulous netherworld? For more than a decade, Hu has backed attempts to bridge that gulf, and it's out of his quest that potentially satisfying description of the Big Bang has sprouted. Hu set off down this avenue by musing about liquids. Imagine tipping a bucket of water over your head. The water is made of molecules that are ultimately governed by quantum theory, but you need not be aware of the details. You know you will be soaked. You could even work out precisely how the water would cascade using the science of hydrodynamics, which existing long before quantum theory. If hydrodynamics allows us to describe fluids without fussing over the fine details of molecules, thought Hu, it ought to be possible to create space-time from atoms of space without first perfecting the description of these atoms. There's more to Hu's analogy than meets the eye. In the past few years, physicists have made models of warped regions of space-time from fluids and found that the two are eerily similar. Taking that together with similarities in the undergoing mathematics, Hu suspects space-time is not just like a fluid, it is a fluid. See cold, dark, and wet. To see what he's getting at, think of water in its three familiar phases: ice, liquid water, and steam. All are made of water molecules, but how these molecules interact varies. In steam, they whiz around, doing their own thing. If they hit a cold window pane, however, they begin to huddle together, condensing, forming gas to liquid. Who thinks space-time can undergo similar phase changes? Without something like condensation, the atoms of space would exist as some nebulous netherworld bereft of time and geometry. See fluid picture. Daniel Oriti, theorist at Max Planck Institute for Gravitational Physics in Potsdam, Germany, stumbled upon this line of reasoning as a young researcher. It offered a new and tantalizing way of making sense of space-time, including, he thought, the Big Bang. But he could not immediately see how to translate the analogy to an idea that could be expressed mathematically. One hint came in 2006 when theorists Thomas Konopka, Fotini Markopoulou, and Lee Sommelin, then all working at the Perimeter Institute in Waterloo, Canada, devised a description of space-time as a complex mathematical network of nodes, each attached to all others like some nightmarish cat's cradle. Though too abstract to fit Hu's condensation analogy, the nodes could still undergo an orderly phase change into something resembling space, with basic features we take for granted like geometry. Inspired by this result, Oriti began to explore whether a similar feat was possible using more established descriptions of the atoms of space. He began with a loop quantum gravity description of the atoms, but then he used a second mathematical framework called group field theory, a version of quantum theory used to describe normal atoms to show how they would condense. It took him several years to organize his ideas, But in 2013, together with Lorenzo Sondini at the Max Planck Institute and Stefan Gielen at the University of Hanover, Oriti showed that group field theory could condense his atoms of space. Granted, they could not tell whether the fluid that emerged looked much like our universe, but it seemed to at least have a size and a shape. It was quite a breakthrough in terms of condensing atoms of space into space-time. Oriti said, "I think we've been the first." Then last year he made a more detailed calculation with Sindoni and his colleague Edward Wilson-Ewing. This time, what emerged looked like expanding space-time of our universe. And there was a surprise. The space-time fluid did not like being funneled into a singularity at the moment of Big Bang. Instead, it wanted to bounce back outwards, rather like the Phoenix universe. Lemaitre would be pleased, but that is not the end, or indeed the beginning of the story. So far, the work has relied on certain approximations, and Oriti believes that once these are examined more closely, there is every chance that the Big Bang at the start of their universe will be neither Big Bang or a bounce. In such extreme conditions, he says, space-time could well have changed from one phase to another, meaning it did not have a definite beginning at all. What we think of as the Big Bang was just the moment of condensation, the big condensation, you might say, or if we are still in rewind, the big boil. So what is the space-time netherworld on the other side of the big boil like? Here language fails, because every question, what, where, how, presupposes concepts that simply would not have existed. You have to think about these atoms of space without them existing somewhere in space or evolving somewhere in it in time, said Oriti. The very notion of time and space has to be constructed out of them. It is as if fish were trying to imagine steam. Other theorists are impressed with Oriti's work. Stefan Alexander at Brown University in Rhode Island calls it a creative feat, but he questioned where the creation of matter fits into the picture, because a universe also has matter in it, right? João Maguejo of Imperial College London also praises the work, but says Oriti and his colleagues might need to make their ideas testable. He should take the bull by the horns and try to make predictions on large-scale structures that will rule out other theories, he said. Oriti has yet to do that, but the wider idea that space-time is like a fluid can be put to the test. In 2014, Stefano Liberati at the International School for Advanced Studies in Trieste, Italy, and Luca Macchioni at the Ludwig Maximilian University in Munich, Germany, studied high-energy photons from the Crab Nebula, looking for signs that they had traversed a liquid-style space. Although the results were inconclusive, the experiments did suggest a path to testing the condensation idea. Still, evidence that space-time is fluid-like does not necessarily equal evidence for the big boil. Maybe space-time was only ever a fluid. To really nail that moment of creation, Oriti must find a consistent mathematical description of the free atoms of space existing before space-time as we know it. That is a mind-bending task, given that notions of time, space, and geometry are hardwired into our brains. In this sense, it's the most radical thing you can think of, says Oriti, but that is his challenge, to be a fish out of water. This is by John Cartwright, New Scientist, on Bended Reality. Please leave your comments, and thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support, and that you find all my content so interesting. You'll find the Patreon account details in the description box below.